Welcome to the second lecture on temporal logics. The last time we introduced linear temporal logic, LTL, which allows us to specify statements or formulate properties about the future. Yeah? So in contrast to propositional logic, where we could only make statements about the current state, LTL in addition provides temporal operators like next, globally, finally, and until that allows us for individual traces of the executed system to say which property should hold. The systems we described in terms of Kripke structures, which were kinds of LTS with only one symbol in the input alphabet, so in the alphabet, and in addition it contains also, the states also have a set of atoms. So the states are annotated with a set of atoms that hold in a respective state. And here I have a rough sketch of a Kripke structure, so I did not draw or include the propositions that hold, the atoms that hold in the individual states, but I just marked the different states by colors. Yeah? And when we have described such a system, in this case, we can loop arbitrarily long in the first state, then maybe we can go to the blue state. From the blue state, we make one step to the green state, and if we are in the green state, we remain there forever. So we can have a trace which has only red states, or we can have an arbitrary number of red states, then the blue states, and then infinitely many green states. That are the traces of this Kripke structure we have here. And the execution, the overall execution, could also be visualized in terms of a computation tree that shows us all possible paths and how they are connected. And what is not possible with LTL is to say, okay, we want to make 3 steps on one trace and then make assertions about all possible branches that can be done at a certain state. Yeah? Because in LTL, we first determine the trace which we analyze, which is a specific execution of the program, and then we analyze this. And this we do for all possible traces. Yeah? If we want to have a kind of formalism that allows us dynamically to make decisions, saying the future is not predetermined, but saying we have a choice, then this is not possible with LTL. And for this purpose, in order to do this kind of reasoning, another temporal logic was introduced, and this logic is called CTL. This is computation tree logic. And in principle, CTL is defined like LTL, so it has almost the same syntax, but the temporal operators are in addition, have to be additionally prefixed with quantifiers E or A. Yeah? So how does this look like? This looks like, so here we have a set of formulas that illustrate how this extension looks like, and now we have several new combinations. So in particular we have 2 variants of each operator. For the next operator we have EXF and AXF, where F is a CTL formula. Yeah? And EXF says that in one immediate state, so in one successor state of the current state, F holds. And AX simply says that if we are now in a certain state, then in all successor states F has to hold. Yeah, so we can now make statements about all successor state, or require that some property should hold in at least one successor state. And in a similar way, we can also extend finally, or annotate finally and globally, so we get exists finally F and always finally F in CTL, and F, so exists finally F, says that in at least one future F holds eventually. Yeah? So this means that there is, from the current state we are in, one path, at least one path, where at some point F holds. Yeah? So we require that at some point in the future this property F holds. And F says that in all possible futures F holds eventually. Yeah? So at some point this becomes true. F becomes true. Then we have EGF, which says, which stands for exists globally, and it says there is at least one path starting with the current state in which F always holds. Yeah. So there is one such path. And always globally says F holds always on every path. Yeah. So no matter where I go, F has to hold. And then we also have the prefixed version of the until operator, which is a binary operator. And this says, so EFUG says there is at least one trace or path on which F holds until finally G holds. Yeah. The important thing is that, as in LTL, G has to hold at some point. So it's not enough that F holds forever. At some point we require G to hold for this operator. And AFUG says that on all paths F holds until finally at some point G occurs. Yeah, this is for just some first intuition what the operators with quantifier mean. We now have to make it more concise because now we have some ambiguities there in this natural language introduction, and therefore we now have a look how we can formally introduce these operators and their semantics such that there are no ambiguities. If we want to evaluate a CTL formula, we do this with respect to a certain state, and we say a CTL formula F holds in a state S, and we write this with this entail symbol if certain condition depending on the topmost connective hold. And the semantics of the CTL formulas is distributed over multiple slides, and I would now like to explain you step by step how the semantics of the different operators is defined. So if we have a propositional operator as the topmost symbol, then we do the evaluation with respect to the current state. Yeah? So we have given a Kripke structure, and this Kripke structure has a state S, and we want to know if the formula we currently consider holds in S, and if the formula is simply top, this truth constant, then it always holds. If it's bottom, then it never holds. If the formula we are considering is an atom, then it holds if and only if this atom P is in the set of atoms of the current state of S. Yeah, so we have to check if P occurs in the set of labels of S, and if this is the case, then it holds. Yeah, and then for propositional logical connectives, the semantics is as usual. A formula not F holds in state S if and only if it does not, if F does not hold in S. Then F and G holds in S if and only if F holds in S and G holds in S. So both of them have to hold. Then F or G holds in S if and only if S holds in F, or S G holds in S. Yeah, so this is like the disjunction, conjunction, negation in propositional logic, and the basic assignment with respect to which we evaluate the formula is given by the labels of state S. Yeah, and in the same way we can also define the semantics of other connectives like implication, equivalence, XOR, and so on. Yeah, that's basically the semantics of propositional operators. Now let's start with the temporal operators. Let's start with the next operator. And here we now need at least one path that starts with state S, or we need all paths that start with S. So this depends on the quantifier type that is used. So a CTL formula exists next F holding a state S if there is a path in the Kripke structure or a trace in the Kripke structure that starts with S, so S is at position 0, and in the state at position 1, F holds. So recall, by pi and then as argument an integer, we can access the state of the respective transitions. Yeah? So in contrast to LTL, we do not have a path on the left-hand side of the entailment symbol, but we have a state, and therefore we also need to get a state here. Yeah? So for if there is a path that starts with S, then so there has to be one path which starts with S and on the first position of so in the next state, after one step, we are in a state where F holds. Yeah? So if we have here this computation tree, or a schema of a computation tree, then we need to have the following situation. We are here in the topmost state, and there is one next state, one successor state where F holds, and F holds is indicated by this red circle. Yeah, and similarly we can define AXF, and AXF is true in a state S if and only if for all paths that start with S, it holds that on the first, on position 1, so in the next state, in the successor state, F holds. Yeah? Important, here we have an implication, so as soon as we have a path with starting with state S, then this condition here on the right hand side has to hold. Yeah, and in the picture here, this means AXF holds if F holds in the two states which are having these red circles. Okay, and in a similar way we can define EFF and AFF. So a formula EFF exists finally F is true in a state S if and only if there is a path that starts with S, and we can find an I such that the I is smaller or equal than the length of the path, in case we are not considering in case we are not considering infinite paths, and at position I, F holds. Yeah, hence we are requiring that there is a path where at some point in the future F holds. And for infinite paths, yeah, it means at the path somewhere there has to be such a state that in which F holds. If we look at the tree, then it doesn't matter to which branch we go, but there has to be at least one branch where we need to reach a state where F holds. And this we have here in the leftmost node that is depicted. Yeah, notice this is an infinite tree, which is indicated by the dots here. Yeah, and for AFF, this holds in S if and only if for all paths that start with S, we can find an I such that at PI, so at position I, F holds. Yeah, and here we now have to look that in every possible path, starting from our current state S, we find a state where F holds. Yeah, and here we have the red dot where F holds, and here we have to go to level 3. Yeah, and here we have to go to the lowest level that is depicted in order to find such an F. Yeah, the important thing is that we find an F. Here we have the semantics of the globally operator together with path quantifiers. So exists globally F holds in a state S if and only if there is a path that starts with S, and for all states on this path, it holds that F holds. Yeah, so we have to find one path in the set of all possible paths on which F holds always. And if the path would proceed here, also on this, in this continuation of the program, there is one path where F always holds. Yeah, this is like picking one particular trace where F always holds. And then for the semantics with an A, so always globally F holds in a state S if for all possible paths starting with an S, it holds for all states that are reachable, that F holds in all of these states. Yeah? So no matter where we go, we only come to states where F holds. Yeah? So for example, here this always globally we can use to specify that something bad should never happen. Yeah, that some invariant should hold. Okay, and now the semantics of the until operator. Yeah, the first variant is with the existential quantifier. Exists F until G holds in a state S if there is a path, as before, which starts with S, and we find a position on this one path such that at some point, at some position, this second formula G holds, and on all preceding states in the path, F holds. Yeah? So we require that at some point G holds, and on all states that lead us to the states where G holds, F has to hold. Yeah, here, for example, in the state S, which is the topmost state, F holds. Then here in the second state on the right, F holds, and then we reach a state where G holds, the green one. Yeah, if already the state here on the top would have been green, this would also be fine. Yeah, and yeah, for the universal quantification, we simply require that on all possible paths starting with S, we find a state where G holds, and we also require that on all states that lead to this state where G holds, F has to hold. Yeah, and this gives us this picture we have here. So we have on every path the red dots until we reach a green dot. Yeah. And yeah, because of the universal quantification, this really has to hold for every state. And again, it is not allowed, or the formula, the until formula would not be true if we have a path or a trace on which F always holds. So in every state F holds, but we never reach G. Yeah? This would not make. This is not on this path the until formula does not hold, because we require that at some point the G has to hold. Yeah, and now by having the semantics of the operators with respect to one state, we can define now the semantics of a full Kripke structure, and we say that a CTL formula F holds in a Kripke structure K, which we write also with this entailment symbol. So we have K on the left and F on the right. If and only if for all initial states F holds. Yeah. So now we do not require that it holds for all paths starting with an initial states, but we say for all initial states F has to hold. Yeah? And here I come back to our example. This is the 2-bit counter with the reset, where we said, okay, as soon as, so we have 3 bits. The first bit is the reset bit, and then we have 2 bits that are that represent the states of the flip-flop. So the first bit is an input bit, and the second bits were characterized by the states of flip-flops. And we realized a counter, and if the reset bit is 1, then the counter simply counts, and it's a modulo 4 counter. And if the reset bit becomes 0, then the other 2 bits are resetted to 0. Yeah? So whenever we are here in any state where the first bit is 1, and we get to a state where the first bit is a 0, then we return either to state 0, 0, 0 or 1, 0, 0. And here we have some properties with respect to this Kripke structure specified in CTL, which I will now explain. And we also agreed that this counter does not have an initial state, so in principle we would have to check these properties for all states, which we now will do. Okay, so the first formula says it always globally holds, so in principle on all states that are reachable from a state, not R implies that in the next state A is false, in all next states A is false and B is false. Yeah? This all globally requires us, no matter which state I use as an initial state, it requires us to check for all reachable state, and in this system each state is reachable from every state. It requires us to check this property for all states, and if R is true, then the implication is immediately true. We do not have to do anything. So for these 4 states here on the top, we do not have to do anything. But if R is false for the states here below, we have to check if AX not A not B holds. And and we see this is indeed true. In no matter in which of these states we are, we can only proceed to states where A is false and B is false. Yeah, so for any of the 4 states below here, AX, not A and not B, is true. Yeah, then here we ask if for every state it's true that in one step A and B can be resetted, so that always globally exists next not A and not B is true. And this is obviously not the case. Why? Assume, for example, we are here in the state 101, and we evaluate this exists next not A and not B, then we would have to check it, for example, for so then in 010 A and not B not A and not B would have to hold, and this is obviously not the case. Therefore, this formula here does not hold. This is in contrast to the formula AG, EF, not A and not B. So here we have a not, we do not have exists next, but we have exists finally. So it doesn't matter how many steps we need to do, we just have at some point to reach one state from any state in which not A and not B is true, and this is obviously the case. We could also have reformulated this property here as AG, EX, not A and not B, asking if after 2 steps it is possible to reach a state where A and B are both false, and this would also be true. Yeah, then here we have a very common pattern, AG, AF, not A and not B. And this pattern says always globally, so this says that in any state that is reachable, in any future, on all possible paths, at some point, not A and not B holds. Yeah, and what does it mean? Yeah, it means no matter in which state I am during my execution, and no matter how I proceed, at some point, not A and not B will hold. Yeah, and this is obviously the case. And the always globally requires that this holds in every state during the execution, and therefore, no, if I arbitrarily long execute the program in any state that I can reach, this holds, and therefore this is an assertion that I can always read the state where A and B are false. And yeah, such a formula is, for example, so very useful in the context of verifying that an elevator will always come. Yeah? So that there is no floor where the elevator will never arrive because of some bug. Yeah, then here we have always globally it has to hold if some precondition is true. This is very similar like the first property we have here. Then this postcondition is true. Yeah? If this is false, then we do not have to check this this right-hand side of the implication. Yeah, so always globally, when we're in a state where not A and not B and R is true, so this is the state 1, 0, 0 here. Then we have to check if in all successor states A or B holds until not A and not B. Yeah, saying if I'm in such a in the state 1, 0, 0 and I do one step, can I return to a state where A and B are both false? Yeah, and this is obviously the case. Yeah, and finally we have quite an interesting formula here. So we have all globally R implies always finally A and B. Here the idea, or first, it's the first attempt to formulate that some property holds on the upper part here. So what I try to say is whenever R holds, then at some point A and B has to hold. Yeah? But unfortunately, this formula does not make sense because the always globally R is independently evaluated from the right hand side, and if I just take this AGR and evaluate it for any state where it has to hold, then it becomes clear that AGR is false, yeah? Because we can always reach a state where R is false. And if this formula here is false, here on the left hand side the implication is immediately true. Therefore this formula is always true, and therefore I cannot make any statements about this upper part here. Yeah, and having LTL, this would not be with LTL it would not be a problem. Yeah, because then I would not quantify over all possible over all branches, but I would first pick a path, and then I would pick the path here, and then I could reason about this path. And otherwise, if I would pick a different path, then the left-hand side of the implication would also be false, like before, and the implication, the overall implication, would be true. But this is only in the cases when I'm not talking about this one particular path I'm interested in, but when I'm talking about a couple of other, when I'm talking about any of the other paths. Yeah, so this is about the example with the 2-bit counter. Here we have several important equivalences which we will later on use to bring formulas into a certain structure. If we have a formula occurring as a subformula in another formula, and we have a formula that is equivalent to the subformula, we may replace this subformula without changing the truth value of the original formula. Yeah, and hence we use these equivalences for modifying formulas, for transferring it into another structure without changing its truth value. We use this, for example, to transform a formula into a negation normal form, meaning that we shift negation symbols inside. Okay, here we have first of all the rules of De Morgan. So this you should know from the logic class. Not F and G is the same as not F or not G. Not F or G is the same as not F and not G. Then we have these rules also for quantifiers and temporal operators. Not AXF is the same as exists X not F. Not AGF is the same as EF not F. And not AFF is the same as EG not F. This means the negation swaps the quantifier type. A universal quantifier becomes an existential quantifier. An existential quantifier becomes a universal quantifier. Globally becomes a finally. Finally becomes a globally. The next operator stays the same. And yeah, we do not have it for the until operator, because for this we would need another operator which I have not introduced. So therefore we cannot shift inside negation for an until operator with the operators we have introduced. Yeah, then F and top is the same as F. F or bottom is the same as F. Then what we have here is if we have B or F, then this is equivalent to P or not P and F, yeah, where P is an atom. F and G are arbitrary CTL formulas. Why is this the case? If P is true, then the whole disjunction is immediately true. If P is false, then F has to be true in order to make the formula true. But if P is false, then not P is true, and therefore the value depends only on the F. Therefore, we can add here this not P in front of the F. Yeah, this looks a bit as if you're making the formula more complicated, but later on we will see that we need this rewriting for transforming formulas into a certain structure. Yeah, then here we have always F until P, where P is a variable, an atom. Then this is the same as not P and F until P. Yeah? because at some point P has to hold, and before that F has to hold. But before that, until F holds, until P is reached, F has to hold, but it's not necessary that P holds, so not P can be true. Otherwise P is true, and then we are done with the evaluation of the until anyways. And we can also formulate this equivalence with a not P on the right hand side of the until operator. So in principle we need to have a literal here. So not P has to hold at some point, and before it F has to hold, and this is the same as P and always P and F until not P. Yeah? So at some point not P has to hold, but before this F has to hold, and also P has to hold, otherwise not P would hold and we would be done. Yeah, and then we can express always finally F as until operator as well, and this is the same as always top until F. So there is no there's only top on the right hand side, which is the formula that is always true, and at some point we have to find a state on all possible paths where F is true. There are many more equivalences. We could also formulate them for existential quantification. We could also, what I did not mention, what also is often used is the elimination of double negation. If we have a formula not F, this is the same as F, and so on. And the equivalences we have here and more equivalences also hold for LTL formulas, which could be very useful. Now that we have these two temporal logics, you might wonder how they relate. So can we formulate a formula that we have in one language also in the other language? And in fact, what does it mean to translate one formula into the other? What does it mean? There is a CTL formula that is equivalent to an LTL formula, because we cannot directly relate them due to the different syntax and semantics. Before we answer this question, let's first think a bit about the difference. So in LTL, we consider only single traces where the events have a linear order, and before we evaluate a formula, we know exactly which states will be visited. So this is like we execute the program and record the states that are visited. While in CTL, the situation is more dynamic. At each state, we can decide which branch we take if we are at a branching point. So in some sense, the future is less predetermined in CTL than it is in LTL. Yeah? And assume now we have one tool that supports LTL specification and one tool that supports CTL specification, and we want to compare the specification. How can we do this? And the question is, can we always express formulas of the one language into the other? Now consider the formula here, which we have seen almost before. So in the previous formula we had always globally R implies always finally A and B, and we came to the conclusion that this formula does not make sense in CTL because of this left-hand side of the application, which evaluates to false on all possible states, and then therefore the application is true. This is different than in LTL, where we consider individual traces, and for the individual traces, the left-hand side can also become true, because we can have a trace where globally R holds, and only for these traces we want to check the property here on the right. So we have an if this holds, then if this property globally holds on the path, then we want to check the property on the right. And something like that is not expressible in CTL. Another important property of LTL is that it is compositional. If we consider the synchronous product of Kripke structures, so if we build the product automated, kind of, as we have done it before, I do not formally introduce it, but just as another important property of LTL I would like to point out. So if we do the cross product of two Kripke structures, and we know that the first Kripke structure satisfies a specification F1, and the second Kripke structure specifies a specification F2, then the cross product, so the automated where they run in parallel, satisfies F1 and F2. Yeah, so we if we have two software components, and or two components could also be hardware, and if we know that for one F1 holds and for the other one F2 holds, and if we plug them together, we know that both properties hold. And here, the second item, we have a variant of this insight. We know that in one component, the formula F holds, and for the first component, we know that if F holds, it follows that G holds. Yeah. And now we can do some kind of modus ponens, and in the synchronous product, it follows that G holds, because F holds in K2, and in K1 it holds F implies G, and so if we combine them by conjunction, then this allows to derive G, and therefore G has to hold the synchronous product of the two Kripke structures. Yeah, and this property is not available in CTL, so here we do not have this compositionality. Yeah, and therefore we come to the following proposition: CTL and LTL have different expressibility, and here I have two examples of CTL formulas that cannot be specified in LTL. Always next exists XP cannot be specified, because this is quite obvious, because in LTL we consider only individual traces, and therefore existential quantification is not possible. So one could ask if CTL formulas that have only always quantifiers in front of the temporal operators, if they have a corresponding LTL formula. And as we will see for this example here, this is not the case. But before we do this, let's make us more concise what it means that the CTL and LTL formula are equivalent or correspond to each other, and then we will introduce some syntactic criteria that allows us to translate one of the formula into the other. So we get a very clear algorithm that helps us to decide whether a CTL formula has an equivalent LTL formula or vice versa. We say that a CTL formula F and an LTL formula G are equivalent if and only if they hold for the same Kripke structure. Yeah, so if a formula F is true in a Kripke structure K, then also G has to be true in K, and vice versa. Yeah. So they have the same value for all Kripke structures. And a bit later we will see some criteria how we can decide if two formulas are equivalent, or if we can even find the equivalent formula or show that no equivalent formula exists. But before we do so, let's have a look at the universe of temporal formulas, which is indicated by this rectangle we have here. So there are more temporal logics than we covered in this course, and there are also extensions of CTL and LTL which we will not discuss. Yeah, so the universe is much larger than just the CTL and the LTL formula, which are now covered here or contained here in two circles. And for CTL, we have a sub-language, ACTL, which is the set of CTL formulas without E-path quantifiers. So we have no existential quantifications in the ACTL formulas, and we also require that the formulas are in negation normal form. Remember, a formula is in negation normal form if and only if negations occur only in front of atomic propositions. In consequence, it is not possible that negation could change the kind of a quantifier, because if we have not always and something, then the negation inverts the quantifier, and we would indeed have an E quantifier and not an A quantifier. Yeah, therefore we require the formulas of ACTL to be in negation normal form. And now a spoiler. We have here a set of formulas which is called CTL det, and the same set contains also LTL det, and these are exactly the CTL and LTL formulas that have a corresponding equivalent formula in the other logic. Yeah, only it can be proven that only formulas in this subset of CTL det and LTL det, only if they are in this subset here, they have a corresponding formula. But let's proceed first of all with the following result, which tells us the connection between ACTL formulas and LTL formulas. This is a result of Edmund Clark and Tracistescu, which they got which they published in '88, so quite a while ago. And first of all, we introduce the following notation. So if F is an ACTL formula, as we have just introduced, then F without A, so F \A, denotes the LTL formula that we obtain from F by deleting all the path quantifiers. Yeah? So we simply remove all the A's from F and get an LTL formula. Here I have an example. GAFP is a CTL formula, and without the A we got GFP, which is an LTL formula. And the two authors got the following result. They proved the following theorem. If we have a CTL formula F, then we can express F in LTL if and only if F and F without A are equivalent. Yeah, so we have to prove this equivalence in order to ensure that F can be expressed in LTL. If we can show, on the other hand, that F and FA are not equivalent, meaning that we can find a Kripke structure for which one formula holds and the other does not hold, then we can conclude F does not have an equivalent LTL formula, no matter how hard we try to find one. And this theorem is proven in this 1988 paper, and a proof sketch can also be found in the old video recording that is available on the FM webpage. Yeah, so if you're interested about about a proof sketch, you find it there in this old video. I just use the result in the following and show you how we can decide if a CTL formula does not have a corresponding LTL formula. Yeah, but the proof is not difficult, and it can also be easily understood by reading the paper. And then you have the concise proof. And yeah, so if we can show that F and F without A are not equivalent, then we can conclude that there is no LTL formula that is equivalent to F. This is what this theorem says. And let's have now a look at an example. Let's consider the formula AFAGP, and the claim is now that this CTL formula does not have an equivalent LTL formula. And this we do by showing that there is a Kripke structure K in which the formula without A holds, but the CTL version of the formula does not hold. Okay, and finding this Kripke structure is a creative process. There we have to understand a bit what these operators do and how they relate. And often these are very similar patterns. So if one has seen this several times, then it's not so difficult to come up with. And we consider, and this is now some creative process. Let's consider the following Kripke structure. We have seen it at the very beginning, which consists of 3 states. In the first state, P holds. In the second state, not P holds. To make it explicit, I have written down not P, because this plays an important role. Usually, we would simply omit this literal. And in the third state, P holds. And in 1, we have a self loop, and also in 3, we have a self loop. Okay, and if we now do the computation tree, then this has the following structure. We have one path where we stay forever in 1, and from every visit of state 1, we can also branch to state 2, and then after one time visiting state 2, we stay forever in state 3, the green one. Okay, and now we have to show that for this Kripke structure FGP holds. A Kripke structure, a formula holds in a Kripke structure if and only if it holds in all states, in all paths or in all traces starting with an initial state. We have only one initial state, so we have to identify all possible traces, and obviously we have infinite many traces, but they are all of the same structure. So one trace is simply the path which we get when we just stay forever in state 1. I write this here now with the omega notation, so we visit state 1 infinitely often. And the other paths work as follows. We do I steps in where we stay in a certain amount of steps. We stay in path 1, and then we switch to state 2, and then we stay forever in state 3. Yeah. Okay, and this we have written down here. Yeah. So we have a finite amount of steps that lead us to, again, state 1, then we do one step to state 2, and then we stay forever in state 3. And now we have to check if FGP holds in on these two paths, and finally globally P. So we have to find one state from which on globally P holds. Yeah, obviously this is the case on the path which has only these red circles, because in state 1 P holds. So if we just consider the trace which goes down, then we find a state, for example the first state, from which on globally P holds. Yeah, because in all states P holds, therefore finally globally P. And for the second path, we do the I steps. So maybe we do 2 steps and end up here. And then we require that finally globally P. So if we just start with this state here, then globally P does not hold because we have the blue circle here. But if we proceed on this path and go to this state here, to the first green dot, then we found a state where we start a path in which globally P holds. Yeah? And this is because here in the green state P holds and we stay forever in state 3, and therefore P holds forever. P globally holds. And therefore we can conclude that FGP holds in the Kripke structure. Now let's have a look what is the situation with the CTL formula. Now we have to check for all initial states if AFAGP holds, and therefore we have to check if the formula holds in initial state, and we have to check for all paths if finally it always globally holds, P holds. Okay, and so we have to check it for this path, and also for the path which goes down there. And if we are now here in this state, for example, or in this state, doesn't matter, and we want to check in this state after, for example, doing 1 step, leading again to a red circle, we want to check if always globally P holds. This is indeed not the case, because it would hold for the path which goes down, but it does not hold on the path which goes to the right, because we have this blue circle, and in the blue circle P does not hold, and therefore we have one path where globally P does not hold. Yeah? So the CTL formula does not hold after doing 1 step in state 1. And the same holds if we do 2 steps, 3 steps, any number of steps. We always have the problem that to the right there is 1 state where P does not hold. And since we have a always quantifier, it all has also to hold on, the formula has also to hold on the path where we just have the red cycles, and there always globally P does not hold because of the branch to the right. Yeah, and therefore we can conclude that for this Kripke structure we have here, the CTL formula AFAGP does not hold. In consequence, we can conclude that there is no equivalent LTL formula for this formula because of the theorem that has been proved by Clark and his collaborator. Yeah, and this allows us now to say when there is no equivalent formula, but it would also be nice to have a criterion which says that there is an equivalent formula and how it looks like. And for this, we now discuss the result by Meidel. And the insight of Ms. Meidel was that there is a syntactically characterizable subset of ACTL that is exactly the set which gives us the formulas that have an equivalent LTL formula, and vice versa. LTL that is the smallest is exactly the subset of LTL formulas which have corresponding CTL formula. And now how is CTL that defined? This is the smallest subset of ACTL, so only A quantifiers, which contains the following formulas. If formula P is an atom, then P and not P is in CTL det. If F is a CTL det formula, then AXF, AGF are in CTL det. If F and G are in CTL det, then F and G are in CTL det. Yeah, so nothing special about this formula. They are included as in full CTL formula. The special thing about these formulas is that we do not get any interdeterminism when branching. Yeah? So there is no choice what we do because it's clearly defined what are the next state, what is globally, and there is not really something where we can either consider this branch or this branch. The situation is different for disjunction and until operator, and also for the finally operator, but we have seen the finally operator can be expressed in terms of an until operator, and therefore we do not write it down here explicitly, but use the equivalence we have introduced before. Okay, so if F and G are CTL det formula, and P is an atom, then a disjunction is in CTL det if it has the following form: P and F, or not P and G. And this is an if then else. If P is true, then F holds. If not P is true, then G holds. Yeah. Otherwise, with just having the disjunction, the formula would be true if F holds, if G holds, or if both true, if both hold. And with introducing this atomic variable and this negation of it here as guards, it becomes clear which of the two formulas F or G hold in a state. And a similar idea we have for the until operator. If F and G are CTL det formulas and P is an atomic formula, then A, P and F until not P and G is in CTL det. Yeah, so we guard F and we guard G by P and not P. Note that we could also switch the negation symbol, so we could also have here on the left hand side not P and P here on the right hand side. That doesn't matter. The important thing is that we at the time we evaluate the formula, we know if P is true or if P is false, and therefore we know if we have to check F or if we have to check G in order to decide if the overall formula, if the until expression is true. Yeah, and only these formulas are in CTL det, and it could be necessary that we perform some rewriting in order to get exactly those formula, to transform a formula which has exactly of this structure. And then we have a similar definition for LTL det. LTL det is the smallest subset of LTL, such that atoms are in LTL det, negated atoms are in LTL det. If F is a LTL det formula, then XF, GF are LTL det formulas. F and G is an LTL det formula, is F and G are in LTL det. And for the disjunction and until, we also introduce a guard using a propositional variable as before. Yeah. So in principle, we have exactly those formula as we have for CTL det, but just without path quantifiers. Yeah. And the nice thing is, if we are able to transform a CTL formula into a CTL det formula, then we know that this CTL det formula has an equivalent LTL det formula, and this is obtained by simply removing the A. And here the intuition is that this construction removes any interdeterminism in the evaluation and restricts the CTL formulas in some sense only to one path, and therefore we have the same semantics as for the LTL formulas, which consider only one path. So we prohibit somehow the branching by using the guards here. And this gives us a very concise way, or a very concrete way of finding an equivalent LTL formula for a given CTL formula, in case there is one. And here I have some example. In the following P and R are atomic variables. If I have a formula AGP, then this is obviously equivalent to GP there, because AGP is a CTL det formula, and therefore we can simply remove the A and have the equivalent LTL det formula. Then AFP, here it's a bit more tricky. Finally, we did not introduce on the previous slide, but when I introduced the equivalences, then we have seen that we can rewrite always finally P as always top until P. Yeah? So this is an equivalence which I can use. Then we can use another equivalence. Since we have P, an atom on the right hand side, we can conjunctively add and not P to the right hand side. This is also an equivalence we have seen before. So we require that at some point P holds, but before not P can hold. If P would hold for earlier, then this would immediately make the until formula true. Therefore we can add the not P on the left hand side. And then we simply add an and top on the right hand side, and then we have the formula of the structure we want to have in order to say, okay, this formula is a CTL det formula. We have here some, we also use the commutativity of the conjunction, but I hope you see that we now have a formula in the right structure, and from this we can conclude that an equivalent LTL formula is top and not P until P and not and top. Then let's look at AGAF P. Here we can now reuse the result from a path and have AG always and the until we found here. So I merge the steps and immediately use this result, and the formula I get here is also a CTL det formula, and therefore we can simply remove the A and have the LTL formula that is equivalent. Now here an example with an implication. We have always globally R implies always finally P. The always finally P we can again replace with the formula we know from above here. So we have always top and not P until P and top. And still we have always globally R implies this until formula. Now we have this implication here and we have to do something. So in the first step we rewrite this by a disjunction, and this you have to remember from the logic class. We have not R or A, and then this universally quantified until expression. So A implies P is the same as not A or B. This you can easily prove with a truth table. Here I did it directly. Okay, and now we're almost there. And the good thing is that we have a not R and R atomic on the left hand side of the disjunction. So what we can do is we can put an R conjunctively to the right hand side, and what we can also do is we can add an and top to the left hand side of the disjunction, and we get the formula always globally, not R and top or R and until as before. And this is now a CTL that formula, and we obtain the LTL that formula that is equivalent by removing the a's. I hope I got the parentheses right here. Yeah, and then you might wonder what happens with AFAGP. And if you try this, no matter how hard you try, you will not find a CTL that formula because the sub-formula we have here, the AGP, is not an atomic formula, therefore you cannot use the trick. And put the negation bit on the other side, because then we would have an atomic guard, and the requirement of CTL that is to have atomic guards for until, and therefore this is consistent with the result we have seen before, where we showed by finding a counterexample, a Kripke structure, that is a counterexample that the AFAGP is not equivalent to FGP. Yeah. So and therefore we cannot transform this formula to a CTL that formula. Okay, and with this I would like to conclude today's lecture. Thank you very much for watching.